Hi, I'm Li from UIUC, and I'm going to present our paper, Deterministic Integration for Volume Rendering. We describe a novel deterministic integrator for volume rendering that is learned for this specialized task. Our integrator speeds up rendering of leaf-like representation significantly, as we need only a small model. Because it is deterministic, there's no variance, such that our integrator reliably reproduces fine spatial details. Neural radiance field represents a scene with the density and the color fields encoded in an MLP. The MLP is learned by comparing renderings with the ground truth. Nerve scenes are rendered using volume rendering, and the volume rendering integral is estimated with the Monte Carlo method, which is stochastic. The integrator is unbiased, but the variance in the integral estimates produce a variety of effects, including losing details. To reduce the variance issue, we use a novel integrator as follows. For a small segment of array, we use Holder's inequality to break the equation to an alpha term and color term, parameterized by the integrated density and color. We split the scene by voxels and decompose the array into segments given by ray-voxel intersections. For each segment, we compute the integrated density and color, yielding its alpha and c, then compose this to an integral estimate. At each voxel vertex, we place feature vectors, then interpolate to form a feature field. And to obtain our segment integral estimates, we apply a learned MLP to the ray integrals of the feature field, which can be obtained analytically. If the MLP was linear, then this would be integrating the fields in their basis function expansion forms, so our integrator is more general. But an important difference is the MLP must be learned. Our experience has been that this integrator is particularly well behaved, and during the training, both the MLP and the feature field are learned to produce the best integral estimates for our application. Our deterministic integrator may have a small approximation error, but it has no variance. A variance-free integrator means that DIVeR does not smooth the density and the color fields to reduce variance, and so it captures fine details as we see. In these shape scenes, DIVeR is able to recover the red lines and shrouds, while some of these structures are missed by other methods. We can also render the legal stars clearly, while the other methods produce blurry results. The scene structures can be easily missed during the stochastic sampling, but our method successfully identifies scene transparent drumheads. Overall, we get significant improvements in PSNR structure similarity and LPICs. These improvements likely follow because DIVeR is very good at fine details. Because the scene is encoded in voxel, we can easily composite different scenes by blending their voxel features, or swap objects in cropped regions by clustering feature vectors. The decoder MLP can be chosen to be small and evaluated fast. With optimization tricks from other papers, we can run our model at real time while maintaining high rendering quality with low storage cost. Here is a demo of our model inferenced on a 1080 GPU, and the quality is as good as offline rendering. Thank you for watching. Please check our paper and code for more detail.